Welcome to Synthesis Workshop. On today's Research Spotlight episode, it's my privilege to introduce Dr. Stephen Crossley, who's currently a postdoc at UC Berkeley in the group of Chris Chang. Stephen got his Bachelor of Science degree from the University of British Columbia before coming to Scripps for his PhD in the Shenvi group, and today he's going to share some recently published work in the area of total synthesis. I was very interested by some of the synthetic ideas in this paper, so I'm really glad that we were able to make this episode happen. Thank you very much for joining us today, Stephen.
Thank you, Matt, for the invitation to present this work. My name is Stephen, and it's my pleasure to share with you our recent syntheses of Picrotoxinin and Picrotin by a late-stage strong bond activation strategy. This work was done during my PhD studies with Shenvi at Scripps Research in La Jolla, California. Picrotoxin was first isolated in 1811 from the seeds of the Anamirtococculus plant of Southeast Asia and India. Confusingly, picrotoxin consists of a 1-to-1 mixture of picrotoxinin and picrotin, its C12 hydrate. Picrotoxinin is a relatively potent convulsant and non-competitive GABA-A receptor antagonist. Picrotin is also a GABA-A receptor antagonist, but is about 50-fold less potent than picrotoxinin towards GABA-A receptors. GABA-A receptors are pentameric, chloride-selective ion channels, which induce hyperpolarization of membrane potential upon gamma-aminobutyric acid binding by allowing chloride ion flow through them, thereby decreasing the likelihood of neuronal firing. They are the main inhibitory ion channels within the mammalian nervous system. By inhibiting chloride ion flow through GABA-A receptors upon GABA binding, picrotoxinin acts as a central nervous system stimulant. Although it's not used clinically for this purpose due to a small therapeutic window, PXN can be used as an antidote to barbiturate poisoning in animals. It's also a useful tool compound for studying GABA receptors and has been used as a stimulant in the development of anti-seizure medications. Importantly, GABA-A receptors have multiple isoforms. There are 6 alpha, 3 beta, and 3 gamma subunits, plus 7 other subunit isoforms, excluding splice variants and point mutations known for human GABA-A receptors. This combinatorial diversity results in an estimated 600 to 800 different GABA-A receptor subtypes. Additionally, these subtypes are heterogeneously distributed within the central nervous system, but understanding why such diversity exists and its function is difficult to probe experimentally, in part due to a lack of tool compounds capable of subtype selective inhibition and to difficulty with homogeneous expression of particular subtypes in model systems. Therefore, small molecules capable of subtype selective GABA-A receptor inhibition would be useful for interrogation of GABA-A receptor neurobiology. GABA-A receptors are implicated in a variety of cognition-related ailments, including Alzheimer's disease and Down syndrome. Moreover, GABA-A receptors are already the molecular target of a number of common anxiolytic and antidepressant drugs, such as the benzodiazepines, which act as GABA-A receptor agonists. Picrotoxinin is one of a number of structurally related convulsants of plant origin, including giadophenolide, anistatin, and O-dibenzyltashironin. The Shenvi lab and others have found that all of these act as GABA-A receptor antagonists, but display variable phenotypes, including in some cases promotion of neuronal cell growth. The Shenvi lab and collaborators are investigating GABA-A receptor neurobiology using these and other polyoxygenated natural products, with the goal being correlation of structure with binding site, ion channel current kinetics, and phenotypic function. PXN, in particular, displays some highly desirable properties for investigation of GABA-A receptor neurobiology. It's water-soluble, orally bioavailable, crosses the blood-brain barrier, and is fairly specific for GABA-A receptors. It's also been used in humans to treat chloroform malaise in the late 1800s and early 1900s, so there is already some data in humans. In light of these attractive properties, we set out to develop a modern route to picrotoxinin, which would both facilitate our biological goals and advance organic chemistry. Picrotoxinin has been synthesized 4 times in the past by some of the premier organic chemistry labs in the world. At the outset of this project, we studied these syntheses to gain valuable insights to inform our own designs. The first major lesson we observed was a strong correlation between the length of overall synthesis and the expediency with which a central stereotetrad was installed, highlighted here in gray. Thus, the Corey lab installed these 4 stereocenters in 6 steps, with an overall length of 19 steps, while at the other extreme, the Yoshikoshi lab employed 26 steps to make this intermediate and required 40 steps to finish the synthesis. This stereotetrad is key because it includes all the CC bonds about the central cyclohexane core. We asked ourselves, why is it challenging to install these CC bonds expediently? The reason we arrived at is that the expedient stereo-controlled construction of the cis-stereo triad is disfavored by sterics. The cis-fused relationship of the C7-C9 cyclopentane to the C15 carbon is thought to arise biosynthetically via an anti-Markovnikov cyclization followed by an oxidative cleavage, which is very hard to mimic. Intermolecular installation of this cis-fused structure is inevitably disfavored by sterics, which favor a trans-oriented approach. The message we took from this inspection was that we should prioritize efficient synthesis of the central stereotetrad. The second major lesson we learned was that thermodynamic instability of the PXN lactones facilitates their hydrolysis and isomerization. This knowledge informed our tactical execution of the oxidation chemistry. For example, treatment of bromopicrotoxinin with potassium hydroxide results in hydrolysis and translactonization to a more stable 2,2,2 bicyclic structure. The Trost laboratory's synthetic efforts towards picrotoxinin similarly revealed this liability, in which dihydroxylation of a late-stage olefin led to the same intermediate. In the absence of the bromoether and in efforts to circumvent this chemoselectivity issue, the Trost lab observed epoxide opening rather than lactonization under alkaline conditions. However, Yoshikoshi's lab found that oxidative lactonization is sufficient to form the desired lactone. In light of these lessons, we prioritize first, stereo-controlled CC bond formation, and secondly, judicious oxidation choreography in our retrosynthetic designs. Specifically, we reduce the oxidation state of picrotoxinin to arrive at this bicyclic carbocycle, which contains 3 sterically and electronically different alkenes. We reduce the C15 lactone all the way to a methyl group in order to circumvent the aforementioned translactonization problems. We envision that the key carbocyclic intermediate, which contains all the carbon atoms found in PXN, would serve as a platform for eventual analog synthesis, and envision that it may arise by annulation of a 4-carbon unit onto Carvone, a cheap chiral pool material. Although our preliminary synthetic plans did not include dimethylation at C5, which would require a late-stage methyl excision to access PXN, we found its use necessary to meet our first priority, stereo-controlled CC bond formation. In particular, our first efforts with trans-alpha-methyl carbone allowed us to form the most challenging quaternary neopentyl alcohol bond and stereocenters via an aldol addition reaction with methyl-2-oxobutanoate. But NOE experiments revealed that this occurred with a strong preference for the undesired diastereomer. In contrast, use of dimethyl carbone as a substrate in the aldol addition reaction led exclusively to the desired diastereomer at C1 with an inconsequential diastereomeric mixture at C9. This dramatic inversion of diastereoselectivity may be attributed to avoidance of 1,3-diaxial strain in the transition state when approach occurs from the bottom face of dimethyl carbone, but not with trans-alpha-methyl carbone. We tried a number of alternative strategies to dimethylation at C5, but all of these were ineffective. For example, we could not generate the extended enolate with cis-alpha-methyl carbone. Installation of a halogen or nitrile at C5 to remove the acidic hydrogen, which prevented extended enolate formation, was difficult to control stereochemically and led quantitatively to aromatization upon attempts to generate the extended enolate with base. And additionally, aromatization presumably occurs via oxyallyl cation formation. Finally, dihydroxymethylation at C5 required 4 tedious steps to make due to the need to crack paraformaldehyde, and the aldol addition reaction still failed. Therefore, we decided that the dimethylation approach was best. Thus, dimethylation of carbone and an aldol addition reaction enabled stereo-controlled synthesis or installation of all 15 carbon atoms present in Carvone. The neopentyl alcohol of the aldol atom is very sterically hindered and rebuffed attempts at elimination with acids or dehydrating agents like POCl3 and Burgess's reagent. But we eventually found that use of thionyl chloride with pyridine and DMAP and acetonitrile and heating led to the desired alpha-beta unsaturated ester in 67% yield. Treatment of this ester with LDA at 0 degrees and warming to room temperature led to vanillogous ester enolate formation and subsequent 5-exotrig cyclization. The unusually warm conditions for this deprotonation are required for cyclization onto the C6 ketone. This highlights another benefit of the extra methyl group at C5 in that it removes an acidic hydrogen. In support of this assertion, use of the minor diastereomer of the trans-alpha methyl aldol reaction failed to cyclize at this step. With the carbon skeleton now set, we weight the balance, so to speak, with respect to the consequences of incorporation of this extra methyl group at C5. On the one hand, it enabled a short stereo-controlled synthesis of the PXN core, but on the other, it would require late-stage methyl excision to reach the natural products. As a student, I thought methyl excision would be a unique challenge and was worth the risk of failure for this reason alone. But it was a comfort also to know that even if we failed, our primary goal of enabling investigation of GABA A receptor biology could still be achieved with this relatively minor modification, so we decided to risk it. To reach picrotoxinin, we planned 3 alkene oxidations, a bromoetherification, an epoxidation, and a dihydroxylation. We also imagined ways to epoxidize and excise the extra C5 methyl group. The first 2 alkenes we wished to oxidize were the most electron deficient and the most electron rich alkenes, but we were unsure of the best sequence order, so we tried both. Fortunately, the first step in either sequence worked well. Treatment of the triene substrate with lithiated TBHP in THF at 0 degrees led to high-yielding diastereoselective epoxidation of the alpha-beta unsaturated esters alkene, directed presumably via the C6 alcohol. Treatment with NBS in THF led similarly to the desired bromoetherified product shown bottom center. This bromoetherification was essential for subsequent lactone formation because it places the molecule in a rigid net axial conformation. However, the second step in either sequence proved frustrating. Treatment of the epoxide substrate with a wide variety of electrophilic halogen reagents failed uniformly to yield even trace amounts of the desired halo ether. Instead, allylic halogenation was exclusively observed. Our survey of conditions included state-of-the-art reagents like BDSB from Scott Snyder's lab and the NXS morpholine HFIP combo from Tanya Goulder's lab, which both promote cationic alkene cyclization over allylic oxidation. Yet BDSB was completely ineffective with our substrate. Our rationale for this reactivity is that the epoxide provides a hydrogen bond acceptor to the C6 alcohol, locking the molecule in an equatorial conformation and preventing the conformational change required for bromocyclization to occur. In contrast, this conformational change is facile with the triene substrate. We therefore were forced to find conditions for epoxidation after bromoetherification. Initial attempts with nucleophilic epoxidation with metylated peroxides led to hydrolysis of the C10-methyl ester and occurred with poor diastereoselectivity. While treatment with DMDO showed good diastereoselectivity, but low conversion and low regioselectivity, and that significant amounts of allylic oxidation of the C7-methylene occurred simultaneously. We eventually found that use of a biphasic mixture of MCPBA with potassium hydrogen carbonate gave the desired product with both good diastereoselectivity and yield. The final olefin is quite sterically guarded, but we found that dihydroxylation with stoichiometric osmium tetroxide could deliver the desired lactone if we use citric acid as an additive, although the reaction still requires 7 days for completion. Sharpless had showed in 2002 that citric acid serves to buffer the dihydroxylation reaction against morpholine formation and acts as a ligand for osmium, protecting it against off-pathway osmium sequestration. I'm grateful to Hum, a former PhD student in the Barron lab, who pointed me towards these excellent conditions. Hung had employed these during his synthesis of thapsigargan. The steric encumbrance of this olefin is evidenced by the exclusive reaction of both DMDO and osmium tetroxide with the electron deficient but less sterically hindered alpha-beta unsaturated ester olefin when the epoxide is not present. Now, to finish the synthesis, all we had to do, quote unquote, was to excise one C5 methyl group and convert the other to a lactone. Although we couldn't find any precedents for such a transformation in the total synthesis literature, nature was more generous. Methyl oxidative excision occurs by iron-dependent P450 enzymes in the conversion of the plant hormones gibberellin-12 to gibberellin-9 via oxygen-centered radical CH abstractions and radical beta fission. We imagined that similar chemistry could work for our purposes. Indeed, we found that generation of iodine monoacetate under a variety of conditions allowed us to effect from 1 to 4 oxidations via oxygen-centered radical formation. These include primary iodide and ether products, a secondary acetate acetal, and a tertiary lactone, in addition to several off-pathway products. The ability to access so many different products at relatively warm temperatures is unusual for these kinds of Suarez reactions. In our case, the conformation of this particular substrate is key in that high torsional strain, which must be overcome to achieve bond formation between the C3 alcohol and the C15 carbon, slows the intramolecular CO bond formation such that multiple CH abstractions may occur prior to CO bond formation. A crystal structure of this alcohol substrate supports this assertion in that the C3 alcohol is 2.92 angstroms away from the C15 carbon. By comparison, the CO bond length in picrotoxinin is 1.365 angstroms. Further evidence for slow CO bond formation comes from reactivity studies. Base-promoted CO bond formation of the isolated primary iodide intermediate requires heating at 90 degrees to occur. However, the same intermediate, but with the alcohol protected with the TMS group, undergoes ether formation at 0 degrees under oxidative conditions. These results suggest that CO bond formation under the iodine monoacetate conditions may proceed via oxidation of an iodide to an iodine 3 intermediate, which is a much hotter leaving group. We optimized reaction conditions to target different intermediates. Notably, use of silver acetate and iodine and methylene chloride at room temperature favored ether formation, but monoiodide formation at 0 degrees Celsius. Use of lead tetraacetate with iodine and calcium carbonate and benzene and air favored formation of 5-methyl-bromopicrotoxin. We imagined that if we could oxidize the methyl group of this lactone product, we would be able to effect a reductive decarboxylation and thereby complete the synthesis. Radical CH abstractions are normally favored in the order that tertiary are better than secondary, which are better than primary. But this order is very much affected by steric electronic and stereoelectronic effects. Although our substrate, 5-methyl-bromopicrotoxinin, has 4 methynes, 2 methylenes, and 3 methyl groups, our analysis suggested that the methyl groups may actually be more reactive toward radical CH abstraction. Our reasoning was that the methynes and methylenes do not benefit from hyperconjugative donation, are sterically more hindered than the methyl groups, and are inductively deactivated. Additionally, rehybridization of the methylene and methine carbons, which normally occurs upon CH bond homolysis to help stabilize nascent radical intermediates, would be energetically costly with our intermediate because of its structural inflexibility. Methyl CH abstractions with chlorine radicals is feasible and shows a preference for oxidation of a beta-methylene over alpha and gamma methylenes in a substrate with methylenes adjacent to a methyl ester. In our substrate, the methyl group we wanted to oxidize is beta to the C15 lactone, but gamma to the C10 lactone. We therefore hypothesized that free radical chlorination could selectively oxidize the beta-methyl group due to substrate bias. Indeed, subjection of the substrate to radical chlorination conditions led to oxidation of the desired methyl group as the major product in a 1.5-to-1 mixture alongside oxidation of the gamma methyl. The third methyl is inductively and sterically deactivated and hindered. It was not oxidized under these conditions. Although we could oxidize this alkyl chloride once more by subjection to the same or similar radical chlorination conditions, we were never able to functionalize these chlorides further. Reductive conditions led to opening of the epoxide and bromo ether, and nucleophilic conditions to the opening of the lactones. In light of these negative results, we decided to pursue an alternative radical beta fission strategy, much, I think, to the happiness of my hoodmate Sophie, who had had just about enough of chlorine in neurotoxins. So, treatment of the ether product with TFDO led to chemoselective oxidation of the adjacent methylene to a hemiacetal in 47% isolated yield and 2.5-to-1 diastereoselectivity. TFDO CH oxidations are thought to proceed either through a concerted CH insertion mechanism or by a radical rebound mechanism involving OO bond homolysis, CH abstraction, radical collapse, and hemiacetal decomposition to liberate trifluoroacetone. In our case, the minor hemiacetal diastereomer undergoes spontaneous epoxide opening due to the close proximity of the endoalcohol to the epoxide C8 antibonding orbital. Subjection of this isolated hemiacetal to the same conditions as those used for ether formation resulted in beta radical fission and formation of a single tertiary iodide stereoisomer, a transformation more generally known as a Suarez cleavage. The mechanism of this reaction is thought to proceed via iodine monoacetate formation and an exchange with an alcohol to form a homolytically labile oxygen-iodine bond. Hemolysis of this bond leads to formation of an oxygen-centered radical, which may undergo beta fission to generate a more stabilized tertiary carbon-centered radical, and abstraction of an iodide atom leads to the observed product. The observation of a single diastereomer in this reaction may be due to avoidance of greater steric interactions upon approach at the concave face of the molecule and avoidance of a 1,3 diaxyl interaction between the methyl groups highlighted in red. Oxidative lactonization conditions under the conditions previously found led to bromopicrotoxinin in 35% yield. Reductive deprotection with zinc dust and ammonium chloride and refluxing ethanol delivered picrotoxinin. Finally, a Mukiyama hydration of picrotoxinin delivered picrotin in 84% yield. The Mukiyama hydration was first reported in 1989 and it is an extremely valuable addition to the chemical synthetic methods literature. It's now thought to proceed via transition metal hydrogen atom transfer mechanism, a hypothesis first proposed explicitly in 2014 by the Shenvi and Herzon labs in JACS. In 1980, prior to the discovery of this reaction, the Corey group required 4 steps: trifluoroacetic anhydride protection of the C6 alcohol, oxymercuration, organomercury to chloride conversion, dehalogenation, and acetate hydrolysis to effect the same transformation. This route was required in order to circumvent facile ether formation between the C6 alcohol and the C11 carbon, which occurs under acid-promoted cationic conditions. Fortunately, Mukiyama hydration conditions, which proceed via radical intermediates, don't suffer this problem. In conclusion, we have developed 13 and 14-step syntheses of picrotoxinin and picrotin, the shortest routes to date. Our strategy is indebted to seminal lessons gained in previous total syntheses, which informed our chief strategic goal of setting the key stereotetrad as efficiently as possible. Tactically, this was achieved by incorporating a symmetrizing extra methyl group at C5, which we subsequently excised using a radical oxidation sequence. To the best of our knowledge, this is the first example of a strong methyl excision in total synthesis. Secondly, we have developed an 8-step synthesis of 5-methylpicrotoxinin, which retains selectivity for GABA-A receptors and represents a new platform for probing GABA-A receptor biology. Our concise access to the carbon skeleton of picrotoxinin is currently enabling investigation of the combinatorial diversity of GABA-A receptor subtypes, work that is ongoing. Finally, this was a team effort, and I'm very grateful to Guanghu, Mike, Hannah, and Ryan for making this project such a pleasure to work on. Guanghu in particular joined the project after I graduated and ironed out the late-stage methyl excision steps, while Mike and Hannah were invaluable at the early stages of our synthesis. Ryan is a brilliant, creative, and enthusiastic advisor, and if you're looking for a synthesis lab to join, I'd highly recommend his. I'm also grateful to the many friends and colleagues from the other labs at Scripps and Scripps, Florida, who shared their time, chemicals, and ideas with us. And I thank NSERC for a PhD fellowship in the NIH, which provided much of the Shenvi Lab's funding for this project. Finally, thank you for taking the time to watch this presentation, and please feel free to shoot me an email if you have any questions about this work. Thank you, Matt, again, for the invitation to present.
Thank you all very much for joining us today for Stephen's talk on this research spotlight. To support this initiative, help us out by subscribing and follow us on Twitter to stay up to date. See you all next time.